Good morning everyone. I'm Karthik Nayak and today I'll present GraphSC, Parallel Secure Computation Made Easy. This is joint work with Xiaowa, Stratis, Udi and Nina from Technicolor and my advisor Elaine Shi. So we store a lot of sensitive information in the cloud. We have our photos, videos, emails and even financial data and medical records stored in the cloud. And the cloud service provider can actually look at this data in clear and infer information from it. They use it for personalized searches, they use it for recommendation systems, and they also use it for targeted advertising. And in general, users do not want to reveal this information, and hence this is a privacy concern. Consider another scenario wherein you have two companies, say Facebook and LinkedIn, wherein Facebook has a graph representing social connections and LinkedIn has a graph representing professional connections. And they want to compute a user's influence in both circles, that is the professional circles as well as in social circles. Obviously, Facebook does not want to share its data with LinkedIn and vice versa. So in abstract terms, these companies want to run certain algorithms, in many cases machine learning algorithms, whereas users in the first scenario and companies in the second scenario do not want to reveal their data. And the question is, can we enable this in practice? Turns out cryptography comes to a rescue and we can use secure multi-party computation to do this. And secure computation ensures that we learn only the outcome. So if we have to use secure computation in this scenario, here are some of the key challenges we face. One, we may want to run a large number of algorithms on our data, and almost all the work that has happened until now has been on improving individual algorithms. So it is necessary for us to take departure from this one-at-a-time approach and offer certain generic solutions. Second, if we have to use secure computation here, we have to convert a program to be able to run on secure computation. And what this means is that you need to convert your program into an oblivious program. And there is a certain cost associated with doing this. And we want this blow-up to be as small as possible. And third is parallelizability. There is a lot of data existing. And even in the insecure world, whenever you want to crunch data, you end up using a large number of machines to crunch them in a short amount of time. And when we add cryptography to it, the computation is even more expensive. And hence it is of paramount importance to maintain this parallelizability when you move from the insecure setting to the secure setting. And here's how we address these challenges. First, in order to offer a generic solution, we have a generic framework for graph parallel algorithms. And these are the same set of algorithms that are dealt by GraphLab and Pregel, whereas these frameworks actually deal with these graphs in clear text, whereas GraphSC deals with them in the secure version. Some of the examples in this class include PageRank, matrix factorization using gradient descent, algorithms based on alternating direction method of multipliers, matrix factorization using ALS, and there exist many more. Second, we convert these programs into their oblivious counterparts efficiently. And for a graph with V vertices and E edges, the total work blow-up that we have is order log V. And if you compare this with a naive solution, the blow-up would be order V for sparse graphs. Third, we do this by maintaining parallelizability. And the depth of a computation circuit is order log V. Just to give you a sense of how our system performs, for this example on matrix factorization, in a CCS 2013 paper, they ran the same algorithm when they ran a program on 4,000 ratings using 32 processors, and it took them 1.4 hours to do so. With our system, we could do it in less than 4 minutes. So to quickly summarize, we have a generic framework for graph parallel algorithms, which we efficiently convert into their oblivious versions while maintaining parallelizability. So moving on, if we have to use secure computation, say you use Gauss-Gabel circuit, cryptographers tend to think of the computation in terms of circuits, whereas programmers tend to think of the computation in terms of writing programs. And hence, it is necessary to convert these programs into Boolean circuits. Turns out an important intermediary in between is the concept of oblivious programs. Intuitively, what oblivious programs mean is that program traces should not depend on the input data. So if you look at this example over here, which is computing binary search, in each iteration, it is accessing this memory location. And this memory location actually depends on the input data and the search query. So this program is not oblivious. Turns out if you have an oblivious program, it is easy to convert it into circuits. And hence, the major challenge lies in converting programs into their oblivious versions. Moreover, the focus of a paper is parallelism, and we intend to achieve low-depth circuits. There exists some prior work on oblivious parallel RAM, which can take any PRAM program and convert it into its oblivious version. However, in general, they have a polylogarithmic blow-up, and it is more of a theoretical feasibility result, and it's not practical. Whereas for the class of algorithms we consider, we just have an order log V blow-up, and it is more practical. So let us see how we can convert these graph parallel algorithms into the oblivious versions while maintaining parallelizability. So what is a graph parallel program? Suppose you have this graph, and every vertex has some data associated with it. And in this paradigm, you think like a vertex. What that means is that every vertex performs some computation based on its neighboring vertices and edges and its own data. And all vertices do this in parallel. There are three primitives in graph parallel algorithms. The first one is scatter. What this means is that every vertex sends some data to its neighboring edges. The second primitive is gather, wherein every vertex aggregates data from all its neighboring edges. For instance, this vertex A adds up 4, 1, and 2 and stores 7 with it. And the third one is apply, wherein every vertex performs some computation based on its own data. So if we have to make these algorithms oblivious, what it means is that we do not reveal the data on the vertex and the edge, as also we do not reveal the structure of the graph. So if you do not reveal the structure of the graph, what it essentially means is that for any edge, you do not know which two vertices it is connected to. And in general, a vertex does not know which other vertices it is connected to or what its degree is. So if you think like a vertex, the naive solution requires you to communicate with every other vertex, which means it's an order V square computation. What we in turn achieve is an order E log V computation, wherein we only have a blow up of log V for sparse graphs. So let me quickly describe how we do this for an oblivious gather operation. Suppose you have this graph, you represent it as a list of tuples, wherein each tuple represents either a vertex or an edge. For clarity's sake, the white background tuple represents a vertex, whereas the gray background vertex tuple represents an edge. Initially, it's stored in any arbitrary order. So if you have to gather information, you gather it from all the incoming edges. So the first step you do is you perform an oblivious sort in such a way that a vertex is preceded by all edges that are incoming on it. So if you look at vertex D3, it is preceded by edges D13, D23, and D43. And now you can perform, if you have a single processor, if you perform a single pass from left to right, you can perform this aggregation. The sort operation requires order E log V time, whereas the single pass requires order E time, which means we can perform the oblivious gather operation in order E log V time. And in comparison, in clear text, you can do it in order E time. If you were to parallelize this, oblivious sort is trivially parallelizable, whereas for the single pass, you can parallelize it using a generalized hypercube sum. Since we are short of time, I will not go into the details of that. You can refer to the details in the paper. To quickly summarize the complexity of these primitives, if you had one processor in the insecure setting, scatter and gather can be performed in order E time, whereas apply can be done in order V time. A naive oblivious solution in comparison would take order V square time, which is an order V blow up for sparse graphs. In our solution, we just have an order log V blow up, and for apply, we take order E time. And since we have a parallel solution, the depth of a computation circuit is order log V. And for apply, it is a constant. A large number of algorithms can be implemented on our framework, and we have implemented the first 4 in this list, namely histogram computation, page rank matrix factorization using gradient descent and alternating least squares. For our experimental setup, we imagine 2 clouds. The first cloud forms the secure computation Gauss-Gabel circuit Gabler, and the second one forms the evaluator. Both clouds run a large number of processors, and there's a one-to-one mapping in between them. There's communication in between Gablers and evaluators, which is not shown here. We consider 2 settings, one in a LAN wherein all Gablers and evaluators are running on the same LAN, and we consider another setting wherein the computation happens across data centers. That is, Gabler is in one data center, whereas evaluator is in another data center, and the communication happens in a wide area network. To quickly summarize our key evaluation results, we ran this histogram example for an input size of 0.5 million. It took us around 34 minutes for 32 processors. By 32 processors, we mean 16 Gablers and 16 evaluators. And over here, input size in general indicates the sum of the vertices and edges of the graph. For page rank, for one iteration and an input size of 128,000, it took us less than 16 minutes. For matrix factorization using gradient descent, for an input size of 32K, we could do it in less than 34 minutes, whereas for alternating least squares, for a reasonable size, we could do it in less than 2.5 hours. So we had these 7 machines in our cluster, and we tried to run an experiment with a large number of large input size. So we could run this matrix factorization using gradient descent on an input size of 1 million, which comes from 6,000 users and 4,000 movies, and this is a movie lens data set. And we ran this on this 7 machine cluster, which had 128 processors, and we used around 500 gigabytes of RAM. And the time taken for this computation was around 13 hours. 2 important things to note over here. One, the previous work which ran the same algorithm could run only 16K ratings, which is 64x size, smaller size data. And if you compare for the same input size, what took them 1.4 hours took us less than 4 minutes. Second, and more importantly, we used only 7 machines here. We believe if we can use larger number of machines, these 13 hours can be dropped down to a few minutes, and that is why parallelization is so important. Moreover, our techniques do not make use of hardware AES-NI, and we believe if we use that, our computation can be even faster. Since I mentioned Facebook and LinkedIn earlier, obviously they are not going to be on the same data center. Their data centers are going to be spread apart. So we ran this experiment for page rank across 2 different data centers. The Gablers were run on Amazon Oregon data center, whereas evaluators were in the North Virginia data center, and the bandwidth provision between them was 2 Gbps. For this graph, on the x-axis you see the number of processors you use, and on the y-axis you see the time taken for the program to run. And the different input lines correspond to different input lengths. And as you can see, as you move from left to right, as the processors increase, the time reduces linearly. So parallelization helps even when you have this computation happening at different data centers. So to conclude, we have GraphSC, which is a parallel secure computation framework for running graph parallel algorithms. And this is built on top of ObliVM, and ObliVM will actually be presented by Chang 2 presentations from now. And our source code is available on oblivm.com. Thank you, and I'll be happy to take questions.
Thank you for the talk. So you started with this motivation of Facebook and LinkedIn wanting to combine their data, which I think is a little frightening, but we'll assume they want to do that. What they would need to do is a little different from what I think you've described, right? So they want to do something that depends on combining the graphs rather than one party having a graph and the other party wanting to do a computation on it.
So with that example, what I had in mind was you have Facebook and LinkedIn. For each user, you have the social graph representing social connections and professional connections. So what you would want to do is, you would want to first perform a union of those two graphs and compute some function like page rank, wherein it will tell you how influential you are. So in that sense, this is...
I see, okay. So you're assuming they first compute a union of their graphs.
Yes.
They have a way to correlate the nodes and
Yes.
edges, and then they can
Yes.
use your tools to do the analysis of it.
Yeah.
Okay, thank you. Other question? Yes.
Hi, Jonas from EPFL. I was wondering if you could go back 1 or 2 slides to where you had the results. This one's, yeah.
This one?
Yeah, exactly. So here you increase your. Okay. Okay, I think it's okay. I was wondering, since when your data size increases by 2, what the corresponding increase in the computation time was.
So it is actually... So it is actually a factor of a little more than 2, because it's, as we saw, it's an n log n computation. Actually, we use Bytonic sort for our implementation. So it's an n log squared n computation. So as you increase the input size by a factor of 2, the actual time it takes increases by a factor of little more than 2. In this particular example, if I remember it correct, I think it's 2.2.
Okay, yeah, thank you.
Okay. Let's thank Karthik again.
Thank you.